All right, let's jump straight into this explainer. If you've been staring at quantum circuits and feeling, completely overwhelmed by all that dense algebra, you are definitely in the right place. Today, we're giving you the ultimate shortcut to mastering the math behind quantum algorithms. We're going to break these complex concepts down just like we're sitting together in an undergrad study group. By the end of this, you won't just understand the math, you'll literally be able to bypass a lot of it completely.
So here's our roadmap for today. We'll start with the quantum parallelism advantage, then look at the phase factor problem and solve it with the phase table cheat code. After that, we'll check out a slick decimal shortcut using ON states, dive into the magic trick that is phase kickback, and finally wrap up with some undergrad practice, where it's your turn to try.
Okay, part 1, the quantum parallelism advantage.
This is where we beautifully contrast classical computing with the sheer weirdness of the quantum world. Imagine you're stuck in a giant maze. A classical computer is forced to use serial processing. It tests one single computational path at a time. It walks down a corridor, hits a dead end, turns around, and tries another. Honestly, it's incredibly tedious. But quantum parallelism, it's like dropping a clone of yourself into every single corridor of that maze at the exact same moment. In our circuits, we do this by applying Hadamard gates across multiple inputs, which basically lets the system execute every possible path simultaneously.
And here's why that is a massive deal. By applying these operations, a system with n qubits explores 2 to the power of n basis states all at once. So think about it. If you have just 2 qubits, you're instantly operating on 4 states, 0, 1, 2, and 3. Add more qubits, and this scales exponentially, like off the charts. It's the foundational engine behind why quantum algorithms can crack certain problems in literal seconds that would take classical computers millennia.
Moving on to section 2, the phase factor problem. So here's where we hit a bit of a snag, the binary dot product. It's this annoying little math hurdle that dictates the changing phase factors of our qubits, especially when dealing with algorithms like Deutsch-Jozsa. Basically, when we apply a Hadamard gate to an input state that isn't just a basic 0, we get a phase shift. To figure out if that phase becomes positive or negative, we have to multiply the binary strings of our inputs and then calculate modulo 2. If the sum is even, you get a 0. If it's odd, you get a 1. Simple enough, right? Well,
the issue comes up with this specific equation, -1 to the power of x dot z. Doing this binary dot product the long way every single time you evaluate a quantum state, it is absolutely exhausting. Imagine doing this for dozens of combinations, you'd be swimming in modulo 2 arithmetic and completely losing the forest for the trees.
Which brings us perfectly to section 3, the phase table cheat code.
To save you from all that complex algebra, I'm going to give you a massive mathematical shortcut. We can build a foolproof phase table step by step, entirely skipping that tedious modulo 2 calculation. Here are the simple rules. Step 1, check the least significant bit, the LSB. If it's a 0, start your sequence with plus plus. If it's a 1, start with plus minus. Step 2, look at the next bit. If it's a 0, just copy whatever signs you already wrote down exactly as they are. Step 3, if that next bit is a 1, you still copy the previous signs, but, and here's the trick, you multiply them by an extra minus sign to flip them. Let's actually see this in action with a 2-qubit cheat sheet. You can instantly map out exactly where the minus signs land based purely on this repeating pattern. Let's trace it. Look at input 1, which is binary 0, 1. That first bit is a 1, so we write plus, minus. The next bit is a 0, so we just copy that exact sequence again. Our final phase row for state 1 is plus, minus, plus, minus. Now look at input 3, binary 1, 1. It starts with a 1, so write plus, minus. But the next bit is also a 1, so we copy the sequence but flip the signs, giving us minus, plus. The final row, plus, minus, minus, plus. Boom! No algebra required. And the really cool part is how this brilliantly illustrates the exact same hack scaling effortlessly to 3 qubits. You can generate all those pluses and minuses for an algorithm in seconds. If you need the phase factor for, say, state 5, which is binary 1, 0, 1, you just follow that cascading logic, start with plus minus, duplicate it exactly because of the 0, and then duplicate and invert that whole chunk because of the final 1. It's basically a fractal of pluses and minuses. Let's keep going. Section 4, decimal shortcut using ON states. What if you're dealing with larger decimal numbers and you don't even want to convert them into full binary strings? Well, think of the qubits as physical light switches. We can bypass the math entirely just by counting how many switches are flipped on for both inputs at the same time. If you have a 4-qubit system, your switch values are 8, 4, 2, and 1. Just break your 2 decimal numbers down into these switch values. We literally only care about the switches that are on for both numbers simultaneously. Ignore everything else. If the number of shared on switches is an even number, your phase factor is +1. If it's an odd number, -1.
Let's do a quick example. Say we're comparing the dot product of decimal 12 and 15. To make 12, we flip on the 8 and 4 switches. To make 15, we flip on the 8, 4, 2, and 1 switches. Now, look for the common states. Which switches do they both share? Exactly 2 common on states, the 8 switch and the 4 switch. Since 2 is an even number, our phase factor is -1 squared, which is just +1. You just solved a 4-qubit binary dot product modulo 2 problem in your head using imaginary light switches. How cool is that?
All right, section 5, phase kickback, the magic trick. Now we arrive at the core quantum trick that really makes algorithms tick. Phase kickback. Normally, operations flow forward, right? But in the quantum realm, phase kickback acts almost like a mirror. Instead of permanently altering the target qubit, the phase information from an unknown function actually kicks backward from the target register right into our control data.
Let's break this down with a concrete example using a controlled NOT or CNOT gate, which, by the way, acts just like a classical XR gate. First, we initialize our target register in a superposition called the minus state. Next, our control bit X interacts with it. If the control bit is 0, nothing happens, no operation. But if the control bit is 1, the CNOT gate triggers and flips our target minus state. Because it's already a minus state, flipping it is essentially multiplying it by -1. And here is the absolute magic. That -1 phase doesn't stay on the target. It gets kicked right back to the original control register. This elegant equation captures exactly how that function's output gets embedded directly into the phase of our original data. The really crucial takeaway here is that the target register remains safely in its minus state, perfectly untouched at the end, while our control data now carries the critical information as a negative or positive phase factor. It's a brilliant transfer of information. Okay, section 6, undergrad practice, your turn. You've learned the cheat codes, so let's put that new quantum intuition to the test. Using our light switch analogy, can you figure out the phase shift for the dot product of 13 and 10? Remember, your switches are 8, 4, 2, and 1. Break down 13, break down 10, find those shared on states. I'll give you a second to think about it. Okay, let's see how you did. To build 13, you need the 8, 4, and 1 switches on. To build 10, you need the 8 and 2 switches on. Did you notice that only the 8 switch was turned on for both inputs? That means there is only one shared on state. And since 1 is an odd number, we instantly know the answer is going to be an odd number, creating a -1 phase shift. And there you have it. You just mentally calculated quantum phase factors without touching a single line of complex algebra. You've officially unlocked the foundational mechanics behind quantum parallelism and phase kickback. So the real question is, how will these brilliant hacks completely change the way you approach quantum algorithm design tomorrow? What algorithmic mysteries are you going to decode next? Until next time, keep questioning and keep learning.